In this lab, we explored motion in one direction, with constant force due to gravity. In this case, the system we examined was a paper ball which was dropped from head height and the surroundings, which is the Earth. Using the assumption that gravity is constant, we can use Newton's second law, which states that the final velocity is equal to the initial velocity plus the force divided by the mass and multiplied by time. I found that with an object as light as a piece of paper, using Newton's second law is a decent way to predict the position of a falling object, but you must take drag into consideration. Otherwise, the predicted position is overestimated. Therefore, there is a net force. This is the video I used to examine the path of a real object when falling with constant force due to gravity. I tracked it using Tracker, which gave me the observed positions versus time. I made the negative y direction point straight down to the ground. You cannot see any forces acting on it, but you can tell the object is speeding up because the distance between each point is increasing between each frame. So the negative force must be greater than 0 in the negative y direction. After that, I went to my VIDLE program and inserted my initial values for my experiment. Next, I put in Newton's second law, which states that final velocity is equal to the initial velocity plus the force divided by mass and multiplied by time, and that the position of the ball is equal to the initial position plus the velocity times time. Now, because I know that the ball is not moving with constant velocity, I have to compute the net force. I wrote weight as the mass times gravity times the unit vector, because force is a vector. When I run this by itself, it doesn't tell very much. But when I compare it to the actual data in a graph, you can see that there is a lot of discrepancy. The model overpredicts the position and the velocity after just under half a second. This model is not close to the actual data. Therefore, there must be something missing from our model. To fix that, we go back to our code. The way to make it more accurate is to change the net force. This is where drag comes in. FD stands for drag force, which opposes gravity. Therefore, it negates some of the effect of gravity, making the net force less. Drag increases with velocity, and to make it fit better, we use the magnitude of velocity squared. We then multiply it by a constant b to make it fit with the observed. I used trial and error to find this value of b. I made the final positions equal by playing with b. Again, looking at this model by itself is not very helpful. Comparing it to the actual data shows that this prediction is much more accurate than the model without drag. However, there is still a little bit of a difference between the actual and the predicted. This shows that our model is not perfect, but it is close. This shows that drag is a major contributor that was missing from my original model. It also shows that while drag slows the object's acceleration, it is not enough to stop it from traveling at constant velocity in this short time window. This means that the force due to gravity is not overcome by the force due to drag, and it continues to accelerate on this window. However, because drag is tied to velocity, this model takes terminal velocity into account as well. At a certain point, the velocity will become great enough that the drag force equals the force due to gravity, and it will no longer accelerate. The model without drag does not take terminal velocity into account. Therefore, according to that model, an object will continue to accelerate, and the speed will go to infinity. Of course, that is impossible, so the drag force is important in predicting the movement of a falling object. This graphically shows that the model with drag has a terminal velocity, because eventually the velocity will be constant. Now, how about we look at if we throw the ball down? So in my code, I set the initial velocity to -20, as if it were released with a negative velocity. I then extended the time window so we could see the effects over a longer period of time. I then used the same time window for a dropped object with no initial velocity. The thrown object goes up to start because the drag is so strong that it accelerates upward to start before going down and reaching terminal velocity. As you can see, these two lines look very parallel at the end, which means that their rate of change is the same, so therefore the velocity is the same. This means that it doesn't matter what the initial velocity is, because terminal velocity will get it back to the same speed. By using Newton's second law, you can predict the position and velocity of a falling object. By using the equation v final equals v initial plus force divided by mass times time, and using the force due to gravity as the force, you can find the theoretical velocity of a falling object. However, in this lab, we found that this is not the most accurate way to predict the motion of a falling object, because this does not take drag into consideration. Therefore, in our force, we must add the drag force, which opposes gravity in this case, and is tied to velocity. Therefore, as velocity increases, so does drag. This lab shows that there is a net force on the paper ball that's falling, even though you can't see the individual forces acting on it.